So this is basically a determinant, right? Right. So, I mean, what I have written is actually a normal determinant of, but since each of the entry in this determinant is itself not just a number, it's a wave function, a single particle wave function. So it's a function in itself. And Slater was the first person to talk about it. That's why we call it Slater determinant. Okay. And you know what simple change will happen if it is a boson and not a fermion, right? So if it is a boson and not a fermion, then the only thing I need to do is I need to make it symmetric, right? So now this simple property of the wave functions should be preserved when you don't use the simple wave function picture, but you use the second quantized notation, right? So that is the basic property. And why do we need second quantization first of all? So you have read something, right? So why do we need second quantization? Tell me. So what is wrong in going ahead with this wave function form and just like you solve the Schrodinger equations, you solve the Schrodinger equation for n particle. And so why do we need this picture? Tell me. Why do you need the second quantized picture, the one which we will do now?
I mean, here in this case only we have a two particle system, but if we got a system where we have a large number of particle,
Hmm.
then we have to face problem by solving Schrodinger equation.
So how does it help by writing it in the second quantized form and not solving the Schrodinger equation?
The second quantization is basically the quantization of field. So
Mhm.
so basically, if we deal with a field and the repel of that field gives a particle, it does not matter how many number of particle we have.
See, the most important thing you will see as we will go ahead is that when you have, say, n large number of particles, okay, in a quantum system, so every particle has some quantum level, right, associated with it. So basically, every quantum level has certain number of particles in it, right? So, and since these particles are indistinguishable, it is not important to know which particle is present in which quantum level. What you want to know is how many particles are present in which quantum level, right?
So,
Because all electrons are same or all bosons are same. So it is irrelevant to ask which boson is present in which quantum level. What you want to know is what is the occupancy of each level. And all the dynamics of the system can be studied in terms of this occupancy of each level. Like how the levels, for example, when you talk about, say, non-interacting fermions, right? Then you can see that all the levels below certain energy are occupied at zero temperature. What do you call that energy below which all the states are occupied for fermions at zero temperature?
Fermi state,
Fermi energy,
Fermi energy.
right? So all the states are occupied below Fermi energy, and all the energy states above Fermi energy are vacant. They are unoccupied. So it's not important to know now which electron is present in which energy level below the Fermi surface, inside the Fermi surface. It is enough to know how many electrons are present. So that tells you the total density of the system. And the total density of the system decides what is the maximum energy that is occupied, which is the Fermi energy. And then when you increase the temperature, you know what will happen, that some of the electrons from below the Fermi energy will go above the Fermi energy because of thermal excitations, and some of the states below the Fermi energy will become vacant. So the entire dynamics of the system can be understood in terms of the occupation of various energy levels or various quantum levels. Okay, and second quantization is a simple tool which helps you in doing this, analyzing this picture. So, so let me now see whether you're familiar with some symmetric properties of the wave function. That's good. So now suppose I try to create this two particle state of fermions using the creation annihilation operators of fermions. Okay, I can do the same thing using creation annihilation operators now. So suppose I define an operator C, dagger alpha 1 R1, and I say if it acts on vacuum, it gives me a state, right? So when I start with a state, if something is not clear, please just stop me and ask, okay? Because we are only 3 people, it's not a big class of 30, 40 students. And I'm doing something very simple. So it's good if I come to know whether you are following it or not. So you understand this definition, right?
Yes, ma'am.
Sitaram? So now write the corresponding equation for the annihilation operator. What should I write for the annihilation operator now? Can it act on vacuum? What happens when the annihilation operator acts on vacuum? What will I get? What do I get when annihilation operator acts on vacuum? Look at me. Basically, it just annihilates the state. So nothing can be done, right? There's no state left, not even vacuum. So where can it act? In a non-trivial manner. So if I act on this state, what do I get? What is ground state here? And if I operate this on some other state where beta 1 is different from alpha 1, what do I get? Huh? What is this? What physics you are using? So what is the meaning of this state? Tell me, what is the meaning of this state? This sketch that I'm writing, a state where you have a particle at position R1 in some quantum level beta 1. Sorry, Sojanya?
Yes.
Yeah, what are you saying?
Now, I am saying that it will be beta 1 minus 1. It
Why
will
it will be
decrease the,
beta 1 minus 1?
it
What are we?
will it will decrease the quantum number by 1 unit.
Just a minute, okay? Quantum numbers are not decreased. So I'm just telling you beta 1 is not alpha 1, okay? Alpha is some quantum level. Let's say alpha 1 is corresponds to spin half up, okay? And let's say beta 1 corresponds to spin down half, okay? Now,
Ma'am, ma'am, actually it will not change anything.
it will not change anything. So if I have an annihilation operator acting on, say, so I'm calling down R1, okay? I have a down spin particle at R1 position. This is my state to start with, okay? And then I am operating an annihilation operator which is C up R1 on that. What will I get?
We get the same state what we had in the beginning.
No, no. So what is the purpose of this C? What does this do? So you have to understand what this thing, what this does, what this operator does. This
Uh,
operator can annihilate, can act only if there is a particle present in this state. Alpha 1 at position R1, then it will go there and annihilate that particle, right?
yes, sir.
So the particle has to be there in that specific state so that the annihilation operator can act on that state and annihilate the particle. Hmm. Now, when we acted this operator on vacuum, why did we get 0? Because there is no particle in state alpha 1 at R1 in vacuum state. So basically, there's no particle, so there's no particle even at alpha 1 R1, right?
Yes, ma'am.
So it gives us 0, right? Now, similarly, if you take a state where you have a down particle and you want to annihilate a up particle, so in that down particle state, in this state, down state, I don't have any up particle, right? This is just a single particle state where the single particle, say the fermion, has a down spin and the fermion is located at position R. Is there an up spin part fermion here in this state?
No, no.
No. So when I try to annihilate an up spin fermion from position R, what will I do? Well, it should just give me 0 because there is no up spin fermion at position R. Is it clear?
Yes, ma'am.
So that is why I'm saying, please read from a book like Fetter and Voleka, which tells you about the basic properties of the operators very clearly and nicely, rather than just reading the philosophy. If you don't even understand how these operators work, then it is of no use, right? Then we cannot go ahead. So this was about fermions, okay? I created some upspin particle or downspin particle, or you can have other higher spin fermions also, and then you can also construct the operators accordingly. Okay? So now I want to create a two particle fermionic state using this creation annihilation operator, right? So this state which we were writing earlier, right? So I want to create it using creation annihilation operators. So how do I do that? How do I create a two particle state using creation annihilation operators? So let's think of a state alpha 1, alpha 2, okay, two particle state. Now how do I write it in terms of creation annihilation operators acting on vacuum?
Say creation operator with a subscript alpha 1, and then again apply the creation operator with a subscript alpha 2,
On vacuum.
vacuum, on vacuum.
Huh. Okay, and then
So basically, they creates a particle at the state alpha 1, and another creation operator creates a particle at the state alpha 2. So we
hmm.
get only one part, and similarly, we have to
Okay, I think there is still a gap in what you people understand. Let me ask you to write a single particle wave function. We did it partially, but we write a state. We wrote a state for the single particle wave function. We did not write the wave function, right? So let's write a single particle wave function. So we want to have a single particle wave function for fermions, right? So first I need to get a single particle state, and for this, as I showed you, we are just going to operate C taker alpha 1 on some vacuum state, right?
yes, sir.
Now how do you get the wave function from here? So now you want a wave function in some
Handle
zero
with
space. So
position coordinate.
basically, right. Now, so this is just the definition, right? Because this basically means it is simply, this is what is the wave function, right? So similarly, you can write a two particle wave function and higher particle wave function, but then how does the statistics will come into the play? Because you have to ensure that the wave function is anti-symmetric. So this is the most important part you have to understand, okay? And since you people told me in the last class that these are the things you have kind of done, at least Saujanya told that he has done it in condensed matter physics course, right?
Yes, ma'am.
So you should brush up these things so that we can go on to more important things. So these are really trivial things, okay? So basically you have to understand that the algebra associated with these creation annihilation operators is related to the symmetric and antisymmetric properties of the wave functions of the bosons and fermions basically. So now let me ask you something else. So you know how to write a single particle wave function and what are the creation annihilation operators. So based on the antisymmetric property of the wave function of two fermions, can you tell me what should be the relation between the creation annihilation operators of fermions? What kind of algebra they should follow and why they should follow that?
Ma'am, they follow anti-commute algebra.
And why is it so? How it is related to the antifermionic property of the wave functions, if it is at all related?
In the anti-commute commutator, we have the antisymmetric property.
No, no, that's you just repeated my question, right? So you are so okay. So first of all, what do you mean by anti-commutator property? Okay, because we have two operators. So let's say you have a C dagger alpha 1 and you have a C dagger alpha 2, and then I take the anti-commutator. So when I put a plus outside, it means it is an anti-commutator, okay? So what it basically means is that, okay, so what this object will be. So when you're saying they have anti-commutating properties between what operators? That's important, right?
The creation and the annihilation operator.
Yeah. So if okay, let me just so now, so what do you expect here to happen? What should it be? You said that they are anti-commutators. So what does it mean here? This is the anti-commutator that you wanted me to write, right? Sitaram, do you know what should it be? You read that lecture notes by Ashok Sen. Maybe it is zero and maybe it is not zero. These are the only two options. So when it is zero and when it is not, at least tell me that. So when if alpha 1 is equal to alpha 2, what it should be? And if alpha 1 is not equal to alpha 2, then what it should be? So how should I write? There is a mathematical function for this, what you just said, right? Yes, so you know it, right? Okay, so this is the anti-commutator property. Now can you derive this relation for me? How do you think we can come to this relation using the fact that we have a fermionic, these operators are creating and annihilating fermionic particles in some quantum levels alpha 1, alpha 2. Why should I believe this, right? From where it is coming? We know that these operators are going to create these fermionic states for us, right? Just like we were writing in the previous slide. So here,
Ma'am, using the harmonic oscillator relation.
harmonic oscillator. All the entire condensed matter physics is about harmonic oscillator. So we wrote these wave functions, right?
Yes.
Using the creation operator. right? So this alpha 1 state can be created by the creation operator C dagger alpha 1 acting on vacuum, right?
Yes.
So this holds true for any quantum state. It has
Yes.
nothing to do with harmonic oscillator. And also we are talking about fermions. Fermions are spin half fermions, say. So then how a harmonic oscillator picture will help us? Harmonic oscillators are bosonic in nature, right? So why do you think spin half fermions will help you? Boson's harmonic oscillator will help you in understanding the anti-commutator property of these creation annihilation operators. Harmonic oscillator operators don't have anti-commutator property, right?
Yes.
Then, so how do I understand this? How do I get this that I have written here? Any idea how to derive this thing and how to obtain the algebra for these operators? See, it's very simple, right? You just have to connect the two things, the definition that I gave you on the previous page and the property of the wave function. So suppose I create this alpha 1 state, right? And want to obtain the algebra for one of these operators on the vacuum state. Can you see it now? Sitaram, you are muted. So I was just showing that you can simply operate a vacuum state, operate this anti-commutator on the vacuum state and see that it is just delta alpha 1 alpha 2 times the vacuum. Understood. So is this the only relation between these operators? I mean, between the annihilation creation operators for fermions? What are the other operators? What are the other relations?
If we can also get the commutation anti-commutative relation for the same kind of operator like two creation operator or two annihilation operator.
So what it should be? So suppose
That that will
I
be
was writing
given.
first. Just a minute. Huh? So suppose we write this. Now what it should be?
It will be zero
It will be
zero.
why it should be 0. Irrespective of alpha 1, alpha 2, will it be 0? Hmm? I'm not saying your answer is wrong. I'm just asking you to give some more information. When it will be 0. Just think, do the same exercise. Try to do the same exercise. If this vacuum state is already here. So if you operate this part on vacuum, what do you get? Which state will you get? Alpha 2, alpha 1, right?
Yes,
And if you operate this part on vacuum, what do you get?
alpha one alpha.
But since the fermions are antisymmetric, these are
So they
just.
cannot stay in the same two fermion cannot stay in a same state.
No, I have not said that alpha 1, alpha 2 are the same quantum levels. Did I say that? They can be different, right? I'm using, that's why I'm calling it alpha 1 and alpha 2. I'm not just calling alpha for both of them. If alpha 1 is equal to alpha 2, of course it is 0. Just by the property of
Pauli
Pauli.
exclusion pin.
Right. But if alpha 1 is not equal to alpha 2, then what? Yeah, so this is using the antisymmetric property, you know that for any alpha 1, alpha 2, it is going to be 0. If alpha 1 is equal to alpha 2, this anti-commutator should be 0 because of the Pauli exclusion principle. And if alpha 1 is not equal to alpha 2, then it is 0 because of the antisymmetric property of the wave function. Okay? So basically, you know all the operation relation for fermions that this object is equal to 0. Anti-commutator operators, sorry, both creation operators, then it is always 0. And similarly, what this should be, what should I write here? If you have both annihilation operators, tell me what this should be, the middle one.
Yeah, also be zero.
Why it should be 0? Can you prove it?
Ma'am, when we acting C alpha one and C alpha two in the vacuum state, then both annihilates their respective particle from the vacuum state, so it will be zero.
Yeah, but vacuum state is not the good state to check this thing, because then whether you have plus or minus, it will always be 0, right? Because the each term individually is 0, isn't it? So you should start with a state like this and then check it. And now you will see that the order of operators matter. So if you operate C alpha 2 first and C alpha 1, then what happens? C alpha 2, before C alpha 2 has to act on alpha 2, C alpha 2 will act on this state, but there is a alpha 1 particle sitting here already. So then you will have to exchange the operators so that they act in the appropriate order. And then that gives you a minus sign. Do you understand what I'm saying?
Can you repeat this?
I'm saying, so Saujanya, you were saying that you just operate this anti-commutator of annihilation operators also on the vacuum state, right?
Yes,
And then it will come out to be zero. But then it will
yes,
be zero both for the plus sign and the minus sign.
yes,
So for the plus sign specifically, it is zero. How do we see that? That you can see only by operating it on a two particle state like this, right?
okay, yes,
So when you operate it here, so now you know that this alpha 1, C alpha 1 will annihilate alpha 1. You will be left with a one particle state, that is alpha 2. Then C alpha 2 will go and annihilate that as well. So you will be left with a vacuum state here, right?
yes,
But when this one is operating on this state alpha 1, alpha 2, then you know you cannot, alpha 2 cannot act on this state directly because there is a alpha 1 sitting here. So I have to write a this state as minus alpha 2, alpha 1 to keep the ordering of the indices same, and then I can operate this object. Is it clear,
yes, ma'am.
Sitaram? Okay. See, these things look trivial, but when you start playing around with the Hamiltonian operators and try to find out the conserved quantities, it's very important because the only way to find symmetries in conserved quantities is you will have to calculate the commutator of various operators with the given Hamiltonian metric operator. So if this algebra is not good, then you will get stuck at every step when you will do that more interesting things like finding the conserved quantities for a given Hamiltonian or finding the symmetries of a given Hamiltonian. So you should make sure that you understand these things properly. So what will happen now if rather than fermions you have bosons? Yeah, so tell me what should I write? Sitaram, tell. Commutation relation between what?
Yes, creation and annihilation operator.
No, we should have allowed Sitaram to say something this time. Okay. So this what it should be. Now Sitaram, you tell me what this should be. And can you prove it now? How will you prove it? How will you prove it? I think you need to read, okay, Fetter and Valika. So next class will be on Monday, and I hope by that time you would have read Fetter and Valika properly. Okay. And you can also read other books like Nickel and Orland if Fetter and Volcker is not available, or Doniak and Sondheimer. But basically try to follow some of the quantum many body physics book or condensed matter physics books for this topic. So with for bosons, there are some interesting properties, right, which are not there for fermions. So, for example, your this operator, annihilation operator, right? Let me call it just alpha. Suppose I act it on some n particle state of bosons. What I'm supposed to get? What will it do to this n particle state? You know, it's for one particle state, of course, it is very simple. I have already shown you. Now I am extending it to n particle state of bosons. For n particle state of fermions also it was trivial because there cannot be more than one fermion in a state, right? So whatever the annihilation operator does to a one particle state, it will do similar thing to the n particle state. But if you have an n particle state of bosons and then you operate this C alpha, then what happens?
And this is alpha 1, C alpha 1.
Let's just call it alpha. I don't know what this alpha is. This alpha can be equal to any one of the alphas written inside the state. So what will happen? It's very simple, right? Of course, it's an annihilation operator. It should reduce the number of particles in the state alpha, right? Now, suppose ith alpha is equal to this alpha, then it's going to reduce the number of particles in that state, right? And how will it reduce? Because it's a bosonic system. Any alpha quantum level can have any number of bosons, right? These are not fermions that you can have either 0 or 1 occupancy of that level. That much you understand, right, about bosons and fermions. So how will it reduce? It will reduce one particle there, but then with what weight? So larger is the occupancy of that state, larger is the probability of annihilating a particle from that state. Right? So it will give you some state, where it has acting, where it has reduced the occupancy of the ith level by 1, but the weight of that state now depends upon what was the occupancy of that level before this annihilation operator acted on it. Are you familiar with this? This is like a harmonic oscillator operator, so that at least you should know. So now tell me what will happen if I operate C dagger alpha on this state. And then what state will I get?
I
Right. So I can just add an extra alpha here in a simpler way along with the earlier state. Right? So n alpha plus 1 now, okay? So when you are creating a particle, then the weight is n alpha plus 1 square root, and when you are annihilating a particle, it is root n alpha. So even if the state was empty to start with, that is n alpha was 0 to start with, you can always create a particle. That is why it is root n alpha plus 1. But if suppose the state was not there, the alpha state was empty to start with, then of course you cannot annihilate a boson from that alpha state. That is why you have a root n alpha here. Okay? And so do you people understand why these n alpha and alpha plus 1 comes when we are talking about bosonic states and they don't come when we are talking about fermionic states? And it's very simple, right? Because for fermions, you have the Pauli exclusion principle. So you can have any alpha state is either occupied by one fermion or it is empty. So Junya just told, right? He was saying that you cannot have more than one fermions in any state. So n alpha is anyway limited to 1. The upper bound on n alpha is 1 when you are talking about fermions. But that constraint is not there when you are talking about bosons. And that is why you have interesting phases like Bose-Einstein condensate states in bosonic systems, but you don't have Bose-Einstein condensation, equivalence of Bose-Einstein condensation in fermionic systems. Okay? So Janya,
Yes, ma'am.
are you okay with this, or you want to add something to this?
Okay, ma'am. This is
This is okay. Are you people even trying to follow it, or I'm just because I can't even see your camera? Okay, you should sit in the class from next time with cameras on if it is an online class. And mobile is not a excuse because you should be coming to the institute and either you should be attending the class from the library or I can arrange a room for you where both of you can sit and do the classes. There are desktops in that room, so you can do the online classes from that room.
ma'am. If I buy something now, so can I put it in the contingency?
That you ask the coordinator, okay? I think from day one your contingency should start, but better ask whether all your formalities, joining formalities are over or not.
Okay, ma'am.
Okay, because only the office people will know whether all joining formalities are over or not. So you ask from them, maybe in the SIRD office or to you can ask. Okay, but I'm
Okay,
saying that you should. It's better if you can come to the campus because there I can provide desktops to both of you. Okay, and then you can sit with the cameras on and it will be easy for me to see whether you people are following the discussion or not because I don't see your faces, so then it becomes a problem. Okay, or at least keep your audios on so that I understand that you're listening and you're following it. Okay, so now using this property of the creation annihilation of operators that we just did for the n particle state of bosons, now can you prove to me what will happen if you have a C dagger alpha C beta commutator? What it should be? So I operated on some state alpha 1, alpha 2, alpha n, okay? Now what do I get? Tell me quickly, what should I get if I operate it? हाँ लेकिन स्टेप बताओ ठीक है पहले करते हैं फर्स्ट यू डू दिस फर्स्ट टेल मी द फर्स्ट टर्म what is this now? Then what is the state? State is alpha, beta, alpha 1, alpha n, right? So you have two extra particles in that state. And now if Huh? Now you operate this. What do you get? Again, of course, these constants are just numbers, so I can write them in any order. And the state is beta, alpha, alpha 1, and alpha n, right? And as you know, that bosons commute. So, I mean, they are symmetry. They have a symmetric wave function. So, whether the wave function, whether a state has alpha first and beta later, or beta first and alpha later, they are basically the same states.
Yes, ma'am.
And that is why if you take the commutator of this for any value of alpha and beta, it is zero. And zero times this state basically. So which basically means that at the level of operator also this commutator is zero.
Zero.
Okay, and similarly you can prove the corresponding equation for the annihilation operators, that for any alpha and beta this commutator should be zero. So the only interesting commutator left is when you have a creation and an annihilation operator, right? Now what this should be, and can you prove it? What this should be? What happened? Sojourner?
Yes, ma'am. May I am doing. So basically, if we expand the sorry, commutator, and then apply on the state alpha 1, alpha 2 up to alpha n, and
Mhm.
then the doing the similar thing. So basically, in the
Yeah.
first term, the
Hmm.
alpha dagger C beta applying on the on alpha 1 up to alpha n state. So
Hmm.
basically, it basically creates a new state alpha and annihilates beta minus annihilates the state beta up to -1. So it will
Okay,
be
somehow
alpha.
mine is opposite to yours, so let's just get consistent because I wrote it that way. So then it will create a state. So actually, maybe better to write, n alpha 1 and n alpha 1 with the occupancy. You understand what I'm saying? So then what we can say is uh, that the alpha state will have one less particle, beta state will have one more particle, and rest of the states will have the same number of particles. Okay, that's better way to write. Then you can easily keep the track of what is happening. And then the second term is that again the coefficients are the same, right? Because you are creating a particle in. No, but then there is a chance that alpha can be beta. Okay, so that's where it becomes important to keep track of the ordering. So if alpha is not equal to beta, let's say, first we write for that. That is a very trivial thing to write because in both the cases you will just have the same states coming, right? If alpha is not equal to beta, I'm saying. Because then I don't have to bother about that the particle which I have created here might be getting annihilated here. So if alpha is not equal to beta, this is of course 0. But what if alpha is equal to beta? So if alpha is equal to beta, that's the more important case, right? Yeah. So for that, what is happening? So because you first annihilate a particle with the weight root n alpha, then you create a particle with n alpha only, because now in the new state, you have n alpha minus 1 particle, so minus 1 plus 1 will get cancelled, so you will have just n alpha. Is it clear what I am doing here? What I'm saying
And
is, if
can you repeat?
yeah, I'm just saying, if alpha is equal to beta, okay, and then I operate it on this state, then what happens? So first, suppose you operate C dagger alpha on this, then I create a particle in the alpha state, right? So the
Yes.
occupancy of the alpha becomes more by 1, rest of the states remain as they were. And then I have to operate C alpha on this state. This is the second term, and there is the first term which I am writing below, which is, oh sorry, this is the first term. I'm sorry. This is the first term, and the second term is C dagger alpha C alpha acting on this, right? So here you are first annihilating the particle from the alpha state, and then you are left with one less particle in that state. Now when you create a particle, since there n alpha minus 1 particle, what you get is again the weight root n alpha. So the total weight here is n alpha. So it's basically the same state, nothing has changed. Only the weight n alpha has come. You understand?
Yes, sir.
And in the first term, since you first created a particle, the occupancy of that level went up by 1. But when you annihilate the particle, the occupancy goes down by 1 again. So the state comes back to what it was, where you started with. And then you get as n alpha plus 1 in front of it.
Yes.
So when you subtract the two, you just get
One.
1 times the state you started with. So it
Yes.
means this commutator is equal to 1 when alpha is equal to beta, and it is equal to 0 when alpha is not equal to beta. Okay. So okay, so now let me go a little ahead and write something for you, and let me see if you people can understand it or not. See, so far what we were writing are the operators with respect to certain quantum level, right? The creation annihilation operators of certain quantum level. But using these operators, you can also generate field operators by basically doing a transformation, right? So for example, you can go from the operators in momentum space to operators in real space. Have you heard of something like this before?
By we have to do the Fourier transform.
Yes, so just like we do Fourier transform on functions, suppose you have been given a Gaussian function or some other function, you can do Fourier transform. You can also do Fourier transform on operators. And you can go from operators in one basis to operators in another basis. So suppose you have an operator which creates a state K1, some quantum level state K1. So basically it is just some A that, sorry, I shifted from C to A, I don't know why, but doesn't matter. You can use any symbol for an operator. Okay. And now you want to find out the wave, this operator in the real space. How will you find out the corresponding operator in the real space? Suppose I want to say that this creates a particle at position x, right? Then how this is related to this operator? So what we will do, suppose we know that the single particle wave function for the kth state in real space is equal to phi k1x. And we know that it is nothing but this, right? We just did it few slides away. Few slides back we did this thing. This is the definition of the single particle wave function in the coordinate space. And how can we create this state x? We can create this state x by operating psi dagger x on vacuum. That's the definition of psi dagger x. Just like a dagger k creates a state here, psi dagger x creates a state here. Right?
Yes, ma'am.
So now you know what is the relation between psi dagger x and a dagger k. So it should be possible to write psi dagger x as sum over k, a dagger k into some phi kx. Do you see that? Why I'm writing it? Does it make sense? Sitaram, Parjanya, any of you?
Ma'am, can you repeat this thing?
No, I'm just telling you two operators, right? One operator is a dagger k, which is creating a particle in some, say, momentum space. Okay? Let's think of some fermion. You can create the particle, you can write a state in momentum space or you can write a state in real space. Right?
Yes.
So a dagger k1 creates a particle in k1 momentum state. Now, psi dagger x is the operator which creates a fermion in the real space. So, psi dagger x acting on vacuum gives you a fermion at position x. That's the x state. Now, what is the relation between psi dagger x and a dagger k? So, you know that there is a relation in the wave function in momentum space and the wave function in real space, which is given by this basically. I mean, the state in the momentum space and the state in the real space, they are related by this wave function, which is just this overlap. Is it clear, this wave function? Suppose I tell you that a fermion has a momentum k. Now, if you want to write down the wave function of that single fermion with momentum k in real space, how will you write it down? You need to know this, right? The single particle wave function in real space. Have you ever written a single particle wave function for anything, any particle? You must have written lots of single particle wave functions, right?
Yes.
Particle in a box, particle in potential well, and all sorts of things, right? So
Yes.
every wave function has a real space index and then it has a quantum level index, right?
Yes.
So that is what I'm writing, right? It has a quantum level which tells you eventually the energy of that particle. And then it has a position index which tells you for that quantum level how the wave function is behaving in real space, right? Whether it has nodes, whether it is, where is it becoming zero and things like that. right? You draw these wave functions all the time for single harmonic, simple harmonic oscillator and particle in a box and other potentials, right? So I'm just writing that wave function here. And now I'm saying that can you tell me a relation between the creation operators in real space and momentum space for this particle? I have actually written a relation between the two operators. This is like a Fourier transform only. As you can see that psi dagger x is equal to sum over k a dagger k, and then there is some weight of that particle being in that state psi kx. See, because only two of you are there in the class, I am trying to teach this thing, okay? Otherwise, second quantization is supposed to be a prerequisite for the condensed matter physics course. Huh? And if you people don't read after giving reference in the first class and then you don't try to think along with me in the second class, how do we go ahead? I mean, I'm just writing something very simple, okay? Let me just write it in a slightly different way. And this simple for way maybe you will prefer, but that is limited to certain forms. So suppose I would have written this, then maybe you would have preferred it more. So are you happy with this form? Yeah, so it is similar to the first. So do you understand any of the two forms, the first one or the new one which I have written? It is just the Fourier transform of the operator. The other earlier one I was writing specifically because I didn't know what is the single particle wave function. It doesn't necessarily need to have a exponential ikx form. Okay, so in this I am telling you that phi kx is equal to ikx. So for most of the simple lattice problems, that's the relation that holds, and that is why you have this simple transform. Okay. Now let me try to go to some more interesting condensed matter kind of stuff because I want you people to take an initiative. See, with two students, actually a class is never a lecture class. Up to three students, we always have a reading course. Okay. So you people have to take the initiative if you want to learn something to read whatever references are given to you, come back so that we can have a fruitful discussion. But if you don't read even in the beginning of the course, that gives a very bad, that's basically a very bad indicator of your interest. Hmm. I don't know why you people are not trying to read. Maybe the time is not enough, that I understand. If you have not read it before, and I hope that by next Monday you people would have read it. Now let me write something. I don't know how much of it will make sense. Just to give you some feeling of this, some models in condensed matter physics. So let me write a Hamiltonian. So we will come back to second quantization after both of you have read from Pater and Voleka or Nagel and Orleans. And any of your doubts we will clarify on Monday. Okay?
Okay.
So now I'm writing something. So let's look at this Hamiltonian that I have written. And let me define for you what Ni is. Okay, now tell me, any one of you, what do you understand by this first term? I think both of you understand. It's a very simple term. Right, Sitaram, can you tell what is the first term? What's the first term do? If you have understood by now what creation annihilation operators do, what the first term does? Tell me what is the significance of the first term that I have written. Hello, am I audible?
Yes, ma'am.
Yeah. Yeah, so Sitaram, tell me what is the significance of the first term that I have written now? Can you see it, this Hamiltonian? Yeah, so what is the first term that I have written? What it does? So let me tell you, I and J are some site indices. So suppose you have a one-dimensional chain of particles and I and J are some sites, okay? And sigma is the spin of the fermion. So sigma, here it can be a upspin fermion or it can be a downspin fermion. Now you tell me what is the first term. And H dot C means Hermitian conjugate. And T is just some constant. U is also a constant, some number. So now you tell me what is the first term. What it does. I'm not able to hear anything. So Ajanya, do you want to tell what is the first term? I'm not hearing anything from Sitaram.
And for this is a basically a one-dimensional chain of atoms, and first
Atoms?
T is
I
the
am not telling you atoms, right? And we are talking about fermions.
one-dimensional chain of fermion, and
Yeah.
and T is the hopping parameter. If we choose any two lattice I, suppose I and J, then the first term basically annihilates and annihilates an fermion from Jth lattice with spin sigma, and creates an fermion at ith lattice with spin sigma.
Okay. Let's suppose choose sigma equal to down, okay, in this equation. And suppose my configuration is this. Okay. I have a down at J, okay, and I have an up at I to start with. This is my state. And now I operate this term, C dagger I sigma, C dagger. So on this state, I operate this with sigma up. Let me operate it first with sigma down. Then what will happen? So you operate it on this state. What will happen now? Tell me. The Cj down will annihilate the particle, down particle from the jth side.
And Ci down basically creates the um,
Particle on the ith
yeah,
side. So what will be the final state after this operation? At I side, I have a down
two
and up,
particle, one is spin up and another is spin down.
and j I will have a hole,
No
an
particle.
empty
Hold.
side, right? This is what will happen. And if I operate C dagger I up, Cj up, sorry, Cj up on this state that we have here, then what will happen? Now, since there is no up particle on the jth side, what this term will do? There is no up particle on the jth side, right?
Yes.
So what will happen now if I operate C dagger up? Because there is a sum over sigma, right? In this Hamiltonian, you see sigma is up and down. So I have both the terms. But I operate it on some state. So in a state, I have suppose either a up or a down on J. I have chosen this state on which in which I have a down on J side. And now if I operate C dagger up, Cj down, what do I get? So Cj down will just give zero because there is no up particle to annihilate on the jth side.
Yes.
And also you cannot create a up on the ith side because there is already a up on the ith side,
So it
right?
will give 0.
Yeah, so the up component does not act on this state, only the down component of this Hamiltonian hopping matrix will act on this state, and it will give me a state in which the particle has hopped from here to here basically, right?
Yes, ma'am.
So, Sitaram, is it clear to you now what this term does? You understand? Let me give one more example to make sure that you understand, okay? So you have C dagger I sigma, Cj sigma, and now let's choose this configuration. So you have a I, you have a J, and so we don't need to worry about what are the configurations on other sides because the hopping is taking place only between I and J. Okay, so I'm telling you only the configurations on this state in I and J. And now let's choose sigma to be up here. Now what will happen? Tell now Sitaram will tell what will happen. Sitaram, what will happen now? Tell me. 1 Cj sigma that will become vacant and then on ith side what can happen? On ith side you already have a up fermion and one down fermion. Now when I operate C dagger up on that what will happen? So you have a C dagger I up on ith side, J you are saying will become 0, right? So this is what you have to do now.
Ma'am, it will cannot able to create another Fermi on either side, so it will
Yeah,
become
because
0.
it already has both up and down. So by Pauli exclusion principle, you just get 0. So basically, this jth particle cannot hop to ith particle because the ith particle already has a double occupancy. This is what we call double occupancy when both up and down are present. Okay. But Sitaram, you are not thinking along with us, huh? I want to give you at least one answer to one of the questions you should be able to give. Suppose I had this state. Now what will happen when I operate C dagger I up, Cj up? Tell me, can there be a hopping or not? Very simple. Just use the simple property of fermions and tell me why it will not hop. Can you annihilate particle from jth side? Is it possible to annihilate this particle from jth side using the Cj up? Mhm. Huh. So it will not hop, right? So what are the possibilities when there can be a hop? The only possibilities when there can be a hop is if you have, suppose you are hopping an up particle, right? The only time it can give you non-zero things are either when the ith part site is vacant, then of course this particle will get annihilated and it will move here, right? Or if the ith site has a down, then again this particle will just hop from here to here to give you up, down, and zero, right? But in any other situation, you cannot have hopping from I to j sites for up spin operator. Okay. Now there was another term in the Hamiltonian that I wrote. Okay, just 1 minute I will take. I know the time for your class is up. This is other term that I have written, right? What do you understand from this term? I have given the definition of Ni1. So first tell me what is Ni sigma? What do you think is Ni sigma? What it does?
Ma'am, it is a number operator.
Sorry,
Number operator.
what do you mean by number operator? No, you're telling the right answer. I'm just trying to get more information from you. So what is the number? What does a number operator do? So if I operate this number operator, what you are saying, on certain state, what will it give me? Let's say sigma is equal to up, then what will I get? How? How do you see that? Because it is C tagger I up, Ci up, right? On that state. So first I annihilate a up particle, I get 0 here. Nothing else is disturbed. All other sites are not disturbed, only this site becomes 0. But then I create it back, right? So I get the same state back. It means the expectation value of this operator in this state is equal to 1. You have a 1 sitting here. So that because the number of particles with upspin here is 1. But if sigma is down here, if I operate Ni down on this state, what will I get? 0. Very good. And if I operate this on some state like this, then what do I get? So there is a sum over sigma now. And you have up and down both, doubly occupied site you have. So what you get here now? 2. Okay, so this part you understand very good. So Saujanya, this is clear to you as well?
No, ma'am. Can you explain summation over Ni sigma?
Summation is only over sigma. It means you look at up and down both. Summation over sigma
Okay.
means that,
Okay, ma'am. I understand.
you understand? Let me just write it
Yes, ma'am.
explicitly. Ni up plus Ni down acting on this, that gives you 2 times the same state, right?
Yes, ma'am.
So now let me go back to this Hamiltonian. So now you tell me what is the significance of this term, what this term does. Let it write again. So the term is U sum over I, Ni up, all these are operators, Ni down. What this term will do, what it tells you. So suppose I operate this term on a state where I have a up on site I. What do I get? If I operate this term, right, U, Ni up, Ni down, 0 because Very good. But if you have something like this on the ISI, then what will I get? Not 1. There is a U sitting here, right? Yeah. So I will get U. So what it basically means is that if you have two particles on one side, and since these are spin half fermions, the only possibility of two particles on one side is that if one is up, the other particle must have a spin down. So if you have any configuration like this, then it cost an extra energy plus U because there was a plus sign in front of this term, right? It means compared to the hopping term, if you have U non-zero, then every configuration where you have a double occupancy on any side, it increases the energy of the state by U. Okay? So this is known as the Hubbard interaction, and what I was writing for you was the Hubbard model. This is the simplest form of the Hubbard model, and why people talk about Hubbard model in condensed matter physics and what kind of physics comes out of it. I will tell you in next class. Sorry. This is the Hubbard interaction term. Okay, so I think just give me a minute. So both of you should actually read second quantization from the reference I have given so that we can go ahead with the course in a more serious manner. I see that you need to learn a lot of things about second quantization. So please read it and then we will do other things. Okay? So do you want to ask anything now? Hello?
Yes, ma'am.
Do you want to ask anything
No.
about the course, about the project or anything? So Sitaram, as far as you are concerned, I don't mind sending you the references for reading even before you get the offer letter if you want that. Okay, if you want me to send references even before you get a formal offer letter, I can do that if you want to start reading up. Or if you want to do it only after coming here, then we wait. It's up to you, okay? But if you want, do you want to move or you don't want to move? Yeah, offer letter is just a formality. It should definitely come, right? When the institute is saying that you have been selected, now it is only a matter of because some 10 signatures have to be collected on that letter, I mean, registrar has to send it and then director has to say, do it. And you know that because of Corona, his institute is working with 50% attendance. So only 50% of the staff go to office every day. So there can be delays because of that, okay? No, no, I'm not asking you to resign. I mean, attending classes doesn't harm you, right? Even if you're attending classes there, that's learning is always good. Okay, because you don't know how the situation will unfold, when you will be able to travel, when you will be able to join. Okay, but the offer letter, I'm saying, is just a formality. And Sajani, do you? I sent you some references.
Yes, ma'am. I have downloaded it, but I will start it from today or tomorrow. I'll
No, no, I'm
read
not
it.
asking you to tell me whether you have read it or not. It's a very advanced thing, okay? I want to know whether you are interested in it or not.
Okay, ma'am. I have to figure out myself because I do not know what to do.
No, the review I have given you is the kind of things you said you were reading with Gotham Sheet and you were excited about it.
Yes, ma'am. Actually, the SSH model I have read from
Yeah,
Gautam sir.
that's what I'm saying. So that is why I gave you that review to read if you want to start. See, the point is not that you read the whole thing and then decide, okay? I think the best thing is you start from somewhere and pick up a topic
Yes,
which
ma'am.
is of reasonable interest to the community, condensed matter community and present. And how do you decide that? You do the Google search on that topic and see how many people are writing paper other than me on that topic, right? So then you know that the community is interested. And if community is interested, then the chances of getting good postdoctoral position after your PhD is more. If you work on problem on which nobody else other than you and me are working, then of course chances of getting postdoc position is
Yes.
very little. Okay. So that is why all the
Okay.
topics I have given to both of you people, like many body localization, and I'm also very much interested in the superconductivity and other, not only superconductivity, actually in the complete phase diagram, getting the complete phase diagram of these twisted transition metal, dichalcogenides, and bilayer graphenes. Okay, I just mentioned superconductivity there, but there are many other aspects to those heterostructures. And but those are not the things which you can start doing immediately. I gave those topics so that students know in which direction their thesis will go if they do start something with me. Okay, because the project has to start from something basic. You cannot directly start doing something very complicated without having a good background.
Yes, ma'am.
Okay, so this review which I have given you is also along that direction. If you just want to touch upon some of the things of topological system, this review will help you in that. And then the other paper I gave you is on topological superconductivity. So there is a concrete, cute, simple model with flat bands, and you can try to learn about how to do at least the mean field theory of superconductivity on those flat bands. Okay,
Yes, ma'am.
so decide about it, and then we'll talk more next in the next class. Okay.
Okay, ma'am.
But please keep read the stuff that I give you. Otherwise, the class will not be interesting. I mean, just with two students, I'm not supposed to teach you like this. You should be reading, and then you should be discussing with me. Okay.
Okay.
And if you want to come to the institute, and I think that's better because you can stay connected to the internet and the library and the journals and the other thing. I can arrange a sitting room for you where there is a working desktop. Okay, so whenever you want, you can at least work there. It will be easier for you to attend classes also. Okay, and the thing which I'm using for writing right now is something called, you can buy it, it's very cheap. It's called Wacom writing pad.
You know what?
Huh? Sorry?
What name you say? What name you says?
Oh, I have written it in the chat box. Can you see Wacom? WACOM. Can you see it?
No, I'm
In the
I'm
Oh, okay, so I'm just telling you WACOM. Okay, so it doesn't cost much. Find out if you have a contingency already starting from now. I just bought it from Amazon, and but it's very useful because then both of us, from both sides, we can write and exchange. Because I'm just writing, but then if you people have some doubt, you cannot write and show me. So if you buy this, then the discussion will become very smooth. And it doesn't cost much, only some 6-7 thousand. And I think you people have a contingency of 40,000 or something annually, so it will easily fit into that. It's a very, I mean, I find it very useful for all the online classes. Okay, so just find out from the office whether you can avail your contingency already starting from this month.
okay, ma'am.
Okay, then I'll see you on Monday. You join the same link. Okay, we can use it for a couple of months. Okay,
Okay.
then bye.
Okay. Thank you, ma'am. Bye.
Yeah, bye.